Welcome to physics with the vectors. Shagaki here, Joey and the vectors. Okay. We looked at this the other day, and we're emphasizing that when you have a graph of velocity and time, you do the area under the curve, or, well, we say curve, but straight lines and portions, and you get the displacement, the distance moved with the direction. Okay? And so negative areas make sense in this context because it just means the negative direction, opposite direction. If you did the slope of these, you'd actually get acceleration, slope of a velocity time. Okay. Speaking of that, the last thing on your handout is what we're going to look at here. And then I've got some more graphing exercises for us to do on a sheet. Okay. So I'm waiting for you guys to get this out. I'll pause the video. Okay, team vector, let's go. So we're getting back to this. This is a distance, or actually I added it north, so it's a displacement position graph. I mean, position time graph, okay? Because I put in north on there, positive will be north. So now it's position. If you do the slope of a position time graph, you get velocity. But I said it was only distance time graph, it would be no direction, I would just say speed. But anyway. These aren't straight lines, and I want to show you what you do. It's a calculus idea. If this was a straight line from 2 to 5, I would just take the slope and you know how to do the slope of the straight line. But with this curve here, you don't have a straight line, so you can't truly do a slope there. You've got to use a calculus trick. And we're not using calculus like it's roughly a calculus philosophical. This is more realistic. Your speeds generally aren't. You don't increase speed with a straight line. It's just easier to interpret. So using the graph, determine each of the following. The average velocity for the first 2.5 seconds, that we can do with a average velocity of 2.5 to 7.5. And then C and D is where we need to use this new trick. Instantaneous velocity points A, B, and C. Okay? So what I'm going to do first is, this is my work from the previous year. I'll just move those out of the way. Average velocity, I'm expecting you to be able to do. You guys remember what average velocity's formula is? I'll remind you. Yeah, you do. Yeah. A and B use this, average B velocity. Here's to put an arrow because it means north or south. Average velocity for the first, that means 0 to 2.5. You're going to use some approximations. Oh, I put blue dots where you're trying to read on this graph, and it's not with a lot of tick marks. You're going to have to come up with an estimate. What is the change in position? First of all, is it negative or positive? You can just tell it too. It's negative. It's going down in position. But if you were to estimate what the change is, and I have a little marking there, right, like that, that's what you're trying to figure out. 0.5. Okay, let's go with negative 0.5. That's actually what I had estimated too. It's an estimation though, because there's no extra tick. So we're going to go negative 0.5 meters per second. Essentially, this is the negative rise. Over a run-up, well, that's you can read precisely. 2.5 seconds minus 0 seconds. So 2. Good on this? Now we know how to use a calculator. It should come out to be decimal too. I forgot one thing though that's important. North. That's to make this a vector. Makes this a vector. So it's going to come out to be negative 0.2. What's the unit when we've got meters per second divided by seconds? And that's acceleration. This is good. But that's not precise because we're doing a straight line estimate there. Average. And that means you're braking or slowing down at an average rate of decimal 2 meters per second every second. That's A. That's a little late. Let's do B then. I'm just changing colors so we can contrast. B is 2.5 to 7.5. We're not doing area here though, we're doing slope. So basically there's a slight curve to that. So the average now it's a drop, it's negative. North, south is another way of saying it. But negative north. What do you guys estimate the difference, final minus initial? It'll come out negative. What is our average velocity in this? I don't think we're that accurate, so let's use 2.3. But yes, that's what yeah. Just so you know where that's coming from, so wanted to do it mathematically, you could use like 1.2 or 1.3. It's an estimate. I wouldn't be surprised if some people like 2.2, 2.4, fine. And we're estimating this position here. I'm taking the difference. And the time span we can do accurately. 7.5 minus 2.5 is 5. So negative. I have it worked out 0.4. What is becoming my problem now? Yeah. You make up for this. Oh, no. Okay. Good question. Fine. Okay. C. Instantaneous velocity. That's the whole idea. When you're driving in a car, science appreciation. When you're driving in a car and you hammer down on the gas, your velocity is changing all the time. We'll get a graph of that. You know that you're going from 0 to 110 kilometers per hour, right? Go by Costco and get another. Okay. There was a point, and it's not a span of time even, it was an instant in time when you were going 97.5 kilometers per hour. You just passed right through it. It's only a point, instantaneous speed. You guys get that idea? Not that you stayed at that speed for any length of time necessarily, you could. So here's what, oh my goodness, this pen is acting up. I just undid everything. What happens? I got my stuff back. I press save. I might lose stuff if it acts up somehow. Anyway. At this point A, before I'd say, just take the slope of the straight line that it sits on, but this is not a straight line. Here's what we have to do. This is where you kind of got to use your imagination with it, the stuckness. That little spot there. I'm going to talk to you a bit about the Earth's surface. This is related. This is the calculus idea. Especially here around Regina, when you go south of Regina, it looks pretty flat, right? It is not surprising that 3,000 years ago, a lot of people, a few hundred years ago, that people were convinced the Earth is flat, it's not round, right? Oh, you're a flat Earther, no doubt. Okay. But you don't really have a lot of direct evidence that this globe is round. Because we're so small in relation to the size of the ball of the Earth, you don't really see much evidence of curve, right? It's out there, but I'm not going to get into it. My whole point is that point A, if I magnify it and look in, and imagine that I was an ant walking on that curve, or something smaller, bacterial dust speck kind of size. This would look like a straight line for that little portion, right? So really what you got to do is take the slope of this small portion that looks approximately linear. And so right around here, like I said, at point A, I'm going to sort of extend that idea of right at A, if it was a straight line, I just take a look at a little millimeter to the left, a little millimeter to the right of what it's doing, and extend that into a straight line because of disappearing. We call that a tangent. Now, don't draw it in yet. I'm going to want you to do it carefully with a ruler. And I got my rulers. There. The best rulers are actually the flat ones you get from geometry kits. I don't have a. I have, so I'd say these are better. If you need to grab one, you're going to return them. Grab it. Okay? And here's how we do it. People need to grab it? Good, grab it. I'm waiting. I'll pause in a minute. Okay, the idea to coming up with a tangent is if you can imagine that little spot was a straight line and extend it and draw it up. You're going to take your ruler. Now I'm going to just put it on. Now what I would do is at that point, and it's an estimation, your tangent line will be a little different than Mariah's and Janine's will be a little different. Because everybody, I might estimate, okay, I'm exaggerating, but I rotate this until I think it's kind of at that spot where this is right on, where if I was a microscopic thing, I would think that's flat. I extended point A to the left and to the right at that angle. And then you draw the line in there. I forget if it's this one. That looks about right. Maybe I think, actually, because I have pre-drawn these. Actually, I think that was for the other one. Actually, I think that was this is the one I used here. Every year I come up with slightly different. And then you got a line, you can do the slope. You're going to do that for A. You're going to draw it and extend it. And like I say, yours will be slightly different than mine. You're going to do that for B. And I have these pre-drawn, but I fiddled around with B. Okay. And then I'm going to do one for C. And then I'm going to do the slopes of them. Estimate. You're going to get. What did I do with my units? I feel awful. Look at this. What did I screw up on A and B with my units? I was still in velocity mode. As in, what were my units in A and B? I've made a mistake. Per. If this is only position. It's only meters per second, not square. Okay. We understand why? Because this is only meters per second. I was still thinking that the previous problems in meters per second every second. Huge mistake. Meter. Okay, I'm going to just straighten that out. That doesn't change the numbers. It doesn't change. Okay. James, you guys are doing this and coming up with 3 different slopes of the lines you have. The person next to you might have slightly different slopes, and that's fun. Go for it. Okay? Draw them in there, do the slopes. That's part C. Instantaneous velocities. Okay. Everybody will have slightly different ones, but I wanted you to practice. That's the whole point. Instantaneous on frozen so. Instantaneous speeds without using calculus requires you to get a tangent line drawn in and then do Now, I'm gonna do these out loud because your slopes will be slightly different than mine, but I'll tell you, I had, for the first one, A, negative decimal 38 meters per second, or else you could add positive stuff. Either one of those. Now, so if you had decimal 4 to decimal 35, you know, that's just fine. Anybody outside of that range? Yeah, what was it? 3, 2, okay, that's fine. Now B, I had about 1 meters per second. So, right, yeah, that's the same. You guys know within reason, it's close to 1, 98 to 10, you know, 1.15. C, I had 0.43. So 0.4-ish, you know what I mean? You guys good with those? You understand this idea and why you would have to use that if it's not a straight line. How does it? See, I did out loud. And then, where is the instantaneous velocity 0? What do you know about the slope of something that's going, not moving? What's the slope of that on the position time? That's the hand motion. Horizontal, right? 0 slope. It means you're not moving. Can you just, without any real calculation, there's three spots where you would have a 0 slope with that tangent there. Where would they be about? Just, no, the bottom of a circle gives you a horizontal tangent with 0 slope. So the bottom of this curve, right, okay, I drew it off. Right about here, I don't know, is that 8.4? Like, what do you guys think? What are the other two spots where, because it's going negative and then it goes to the positive, the only way to switch directions is to stop momentarily. So, G. T equals, I forget which one I already did, 8.4. What are the other two times that we'd have 0 speed or velocity, either one? They're actually weak questions. What are the other times? Yeah, but that doesn't help. Put it away. Hey, we're working on this, right? Where's yours? One. Okay. You weren't on Google Plus. Okay, anyways, continuing on. What are the other two times where you have a speed velocity is approximately 0? You're looking for where it bottoms out and tops. Yeah. Can't jump? Yeah, right on the right-hand side of CD and then on the left. 14 and I'd say maybe 14.4. I'm just, this isn't precisely measured yet. And the other spot is on the left side. I don't know, is that 12.5 or 12.4? Like, you come up with that. But what you're looking for is horizontal tangent. That's on a position time graph. That's where you get zeros. Okay? Are we cool with that? Okay then. I'm going to get you the next task. Okay, I'm going to look at these two questions with you. 2 pages, 2 graphs. 2 questions. Shouldn't take you very long. Should be perfect for the end of the class, 17 minutes. Okay. 6, yes. Okay. In the space provided below, create a velocity time graph for the event represented by the position time graph. I have, okay. So what we're going to do is take this information here and I have the answers up there, but you guys get it. I didn't give you guys the answers anyways. Okay. Anyways, so what you're going to do is you want a velocity time graph, you got to figure out what that slope is, right? You guys know how to do a slope. And your answer is going to look, and you'll see it there. Well, 100 divided by 5 is 20. You're going to start out at 20. Now, I have abrupt changes. This isn't realistic, but it's amazing. The next one is going to be a negative slope. You're going to figure it out. You're going to jot it down right there. You follow this? You're going to go from position information to velocity information. You're going to make a graph. Your graph is going to look blocky like this. And that's fine. That's every time there's a change in slope, you're going to have a hard turn on your velocity time. Okay. The other graph is like this. I'm giving you the velocity, so on a position time graph, that is your slope. Right? You're initially going, what's that, 80 kilometers per hour? For half an hour or something like that. Right? So, depending on your scale, you go 80. And then you're going 0. So then, position time, you're staying at the same thing, right? And you know your slope is now 120 or something like this. So if the first one was 80, 0, then this one will be steeper for that length of time. You guys see what you're doing? You could do it that way, or velocity time. How do you find the distance traveled? Under a velocity time graph. How do you find distance? Displacement. Come on, y'all. You work through this on the train. Velocity graphs, how do you find displacement? What do we do on the train graph? Grade 8 math, 6 velocity time. Look at the units when you do the area. In 0 and that spot. That, what, remember on the train graph, we did the areas of triangles and rectangles? Find displacement? That's another way. In the first 30 minutes, so that's half of an hour times 80 kilometers per hour. And you could say I traveled 40 kilometers or whatever you calculate, right? Here, it's at the 0 line, so there's 0 area. So you're going to just stay still. Here you got another area. Here you got this area. This area. It's always area to 0. So that's a negative area down here. Right? So if you guys follow me, find your displacement. Put it onto your position. You could do it by slopes, but I would say it's better to do it by figure out your area, then plot it. It should look something like this. Oh, I traveled 40 in the first 30 minutes, and then connect the dots. I didn't travel anything for this, and then connect the dots. So, just follow what I'm saying? Science. You're in a science classroom. Correct. You blessed yourself. A priest or something?